In this problem, we have water in an open source tank is pumped to a second destination tank at a rate of 5 pounds per second mass flow rate, with the water level in the destination tank 25 feet above the water level in the source tank. We're also told that we can assume that the water level does not change with the flow of water. That is, in both of these tanks, the levels stay relatively constant. The destination tank is under a constant 30 psig pressure. So that's 30 pounds per square inch gauge. Remember, we're told that the first tank, the source tank, is open to the atmosphere. The pump efficiency is 75%. We're told we can neglect friction, and so this means the friction in the pipes and the entrances and exits and fittings and bends. We're also told that we need to determine the required horsepower of the pump and then determine the pressure increase provided by the pump. And we're told that the suction and discharge lines are of the same diameter. And so what I've done, here's our diagram and our given information with our mass flow rate, our efficiency, our pressures, density of water, and our elevation. One of the things we need to think about is what kind of pressure are we going to use. We were told that the pressure in the destination tank is 30 psig. And the source tank is open to the atmosphere. We could use either absolute or gauge pressure for this problem. It's up to us to choose. I am going to use gauge pressure because what that does is that makes the gauge pressure at position 1 0 psig. And so that just seems a little more straightforward to me to do it that way. We're told that the pipe diameters are uniform in the system. We're also told that the levels in the tank do not change very much with time. And so what this means is that the velocity, if we were to apply the Bernoulli equation to the water here in the source tank and at the destination tank, the velocity terms in the Bernoulli equation would go to 0. And I want to make the point that even if the levels were moving, this were decreasing and this were increasing, the velocity terms would still be quite negligible, and we could probably pretty easily neglect those velocity head terms depending on how we apply the Bernoulli equation, or if we were applying the Bernoulli equation to these tanks. Also, we're going to assume that this height difference stays the same throughout the problem. And then finally, water is a liquid at these conditions, and so it is incompressible. And again, that makes things a little bit easier for our calculation. So, all that, what do we want to find? First thing that we want to find is the pump required power. And so to do that, we can apply the Bernoulli equation. And there's several ways that we could apply it, but I think the easiest way to do this is going to be to apply from position 1 to position 2. And so we bring over our general form of the Bernoulli equation, applied from position 1 to position 2, and here is our Bernoulli equation here. And what we are going to do is we are going to now look at our system and the equation and think about what terms we can use, what assumptions we can use to simplify this equation. So the first thing that I have written here is that the velocity terms go to 0. And this is true, again, because the velocity at position 1 and the velocity at position 2 are not changing. We are told they are not changing at all. But again, generally with large tanks like this and much smaller pipes, the velocity between, say, position 1 and 3 would be very, very different, and the velocity at position 1 and position with respect to the velocity of position 3 would be essentially 0. So that's something to remember when you do Bernoulli equation problems with tanks. Next thing we'll do is we'll set the datum, our baseline elevation, to this height here in tank 1, so we have a difference of 25 feet. We are also told that we can neglect friction losses, and so that means that the head loss is equal to 0. Also, of course, there's no kind of turbine or expander here extracting energy, so that is going to go to 0. Note that we need to find the pump required power, the pump power, and so that is going to be captured in the head added term. So that is what we're going to solve for. And so then what we can do is we can go ahead and start working this problem. Let's cross out the terms, simplify it. I'm going to work the problem in SI units, and we'll convert to imperial units as needed for the final answer. So we take our terms and we cross them out based on our assumptions. So the pressure, P1 term, that goes to 0 because we are at 0 PSI gauge. Our velocity term goes to 0. All we're left with on the left-hand side is Z1, which is actually 0. I left it there, plus our head added. Then we look at the right term, the right side of the equation. What terms do we need? We need the pressure because we have 30 psi g. Our velocity term goes to 0, and then we have our elevation term. And so we can simplify this and rearrange to solve for our head added, which is what we want to solve for. And we get a value of 28.7 meters or 94.2 feet. So this is the amount of head that the pump is going to add to the water to get it into this tank. We are asked though to solve for the horsepower. So how do we convert head, which is units of length, to horsepower? And so I always like to remember this. The head added, and again I like to think in SI units, the head added is the energy extracted per unit weight of the fluid. Or we could say the energy added per unit weight of the fluid. And in SI units, meters is the same as joules per Newton. And so you can do the little dimensional analysis to convince yourself of that. If we want to add the energy extracted per weight of fluid, we want to get the total energy added per volume. What we would do is we would take the head and multiply it by the weight of the fluid. And so the weight of the fluid, not the mass of the fluid, but the weight of the fluid is rho g, the density times the gravitational constant. So now we have the energy added per volume of the fluid. And so to get the total power added, we take the energy added and we multiply it by the volumetric flow rate. So meters cubed per second. And that will give us the power in kilowatts or in horsepower. And so what I do is I've got this worked out step by step. You don't have to do this step by step, but just to illustrate, I can type our head added and I can just ask MathCAD to change the units, and you can see that meters is the same as joules per Newton. I then take the head added, I multiply it by rho times g, the density times the gravitational constant, and you can see I get an energy added term with kilojoules per meter cubed in SI units. If I want to then just put this over, if I want to then calculate the horsepower, what I am going to have to do is calculate the volumetric flow rate of the water in this system. And so if you remember, the volumetric flow rate is equal to the linear velocity times the cross-sectional area. We do not need to use that. What we have is we have a mass flow rate. Another way we can calculate it is by taking the mass flow rate, which is given to us, and divide it by the density of the fluid. And so we can calculate a volumetric flow rate of our water through this system, and then we take that and we multiply that by the energy added, and you can see we get our answer either in watts at 638.6 watts or in horsepower at 0.856 horsepower. Now that's not the final answer though. This is the horsepower required to get this fluid moved from one position to the other. We were told that our pump is only 75% efficient. So what that means is our pump is going to require more energy, more power than what is simply required to move the water. And so what that means is we are going to have to divide, because we're requiring power. We're going to have to take this power that we calculated here and divide by the efficiency. And so the actual power that the pump requires to move this fluid is going to be 1.142 horsepower. Now the second part of this problem asks us to find the pressure increase that is provided by the pump. And so if we go back, let's get here our schematic here. The pressure increase provided by the pump. So the pressure at 3 is going to be less than the pressure at 4. And so what we can do here is we can apply the Bernoulli equation across the pump and from position 3 to position 4. And so if we take our general Bernoulli equation, I've got it written in 1s and 2s here, but you can convert to 3s and 4s. We can apply this across the pump, and we can take a look at now what things we can cross out, what assumptions we can make to simplify this calculation. So the first thing I have written here is we can cross out the velocity head terms at the inlet and the outlet pump of the pump. So the question is, how can we do this if the velocity is probably significant, or at least not insignificant? And the reason we can do that is because the linear velocity at position 1 is going to equal the linear velocity at position 2, and that is because our pipe has the same diameter. Our inlet and our outlet pipe has the same diameter. So our velocity terms will cancel out. Also, most pumps, there will be a slight elevation difference between the inlet and the outlet, but that elevation difference is very small, and so we can neglect the elevation head terms. We are not told anything about the head loss or the head extracted. We're going to neglect those terms. And so that is what we're left with. We're left with the pressure at the inlet and outlet, and then this head added. So remember, this is the amount of head that is added across the pump. We have already calculated that up above. What we're going to have to do is convert that to pressure. So we apply these assumptions, and then we simplify this equation, and here's what we're left with. All the other terms are going to cancel out. The head added, as I note here, was calculated above. We just left that as head added. What we're going to have to do is convert that to pressure. And so let's do that. It may seem a little daunting, but it's not that difficult. We just simply rearrange this equation, and our pressure difference, our delta P, is going to be P4 minus P3. This is the outlet pressure minus the inlet pressure. And then we have the rho G that we have to deal with. And so I have defined our pressure drop, our delta P, I should say, as P4 minus P3. And so we can then just solve for delta P, which is equal to the head added times rho times G. And what you can see is that our units work themselves out. We take the head added, we multiply it by the weight of the fluid, and we get units of pressure, 40.8 psi. So that is the pressure increase of the fluid across the pump. Note that we do not have to factor in the pump efficiency. All right, all we needed was the head added. Remember, the pump efficiency is taking into account the inefficiencies of the drive, the drive shaft of the pump and the motor of the pump. All we're worried about is what's going on in our fluid. Another little note here is that the pressure drop is the same as the energy added. All we're doing, like I said here, is just converting our energy units from things like joules per meter to psi. And so all I've done is just taken this and shown that we get basically the same number depending on just how we want to express it. So that's the application of Bernoulli's equation to calculating the pump power and the pressure increase or pressure drop across a pump required to move water from one tank to another pressurized tank at a higher elevation. Some simplifying assumptions to make it a little easier. Specifically, we're neglecting friction, but that's where we're starting, and that's how you do these calculations.